Welcome to the world of the 7QC tools, the essential problem-solving toolkit of Six Sigma. In this video, I'll explain each tool step by step, and together we'll use them to solve the problems in our coffee factory. By the end, you'll see how these simple but powerful tools can transform chaos into control and defects into delight. I think of the 7QC tools as a doctor's diagnostic kit. They don't fix problems by themselves, but they help me analyze and diagnose what's really going wrong. You probably have already used one or two of them before solving normal work problems. These tools are the flowcharts, the check sheets, the Pareto charts, the cause and effect diagram, also called a fishbone, the histogram, the control chart, and finally, the scatter diagram. Now that we know what the 7QC tools are, let's dive in a bit deeper and put them one by one into action. The first step in any quality project is understanding the process, and this is where the flowchart come in handy. I personally think that understanding the process is one of the main keys to solve any quality problem. So, let's try to use the flowchart to describe the process in our coffee factory example. Here's our coffee production process. First, we roast the beans, then we grind them. After that, we weigh and fill the bags, then we seal them and label them, then packing, at the end, shipping. The flowchart makes each step visible. Immediately, we can see possible trouble spots. These spots, or possible problems, could be that the roasting step might cause flavor variation. The grinder could produce inconsistent sizes. The filling step could lead to underfilled bags. The sealing machine could fail to close bags properly. Notice that the flowchart didn't solve the problems, but it gave us the roadmap for where to look. Now that we understand the process, we can move on to the next step, tracking the defects. But for that, we need a real, numerical data, instead of relying on vague complaints. To do so, we use our second QC tool, the check sheet. This is how it goes. Let's say that we want to track the defects for the last week, so the factory supervisor tallies every defect found. Here they are. We have 40 underfilled bags, 25 broken seals, and 15 wrong grind size. Then we take this information and fill them in a simple check sheet that looks like this. Now the issues are no longer random anecdotes, they're measurable facts. Now we can even add more info to the check sheet, like the time and date of each defect, or the production line number. The check sheet is simple, just a tally, but it's the foundation of data-driven improvement. Okay. So now that we tracked all the defects using the check sheet, we can now move to the next step, which is fixing the problems causing these defects. But wait, where do we start? We can't fix everything at once. And that's where the Pareto chart comes in. A Pareto chart is a special type of bar charts used in quality improvement. It basically helps you focus on the vital few causes of a problem, instead of spreading your energy across the trivial many. It is based on the Pareto principle, also called the 80-20 rule, which means that roughly 80% of problems come from 20% of causes. So if you fix the most frequent or impactful issues first, you eliminate the majority of your problems. Okay? So now we have some sort of idea. What does Pareto chart means? Let's now try to actually draw one. Okay? So we start by drawing a simple bar chart of our defects with the defect name on the x-axis and the defect frequency on the y-axis. Notice that I draw the largest defect on the left side, so the bars are basically getting smaller from the left to the right. Okay, so till now, what we have is just a simple bar chart. The next step is what matters the most, which is the cumulative line. The cumulative line shows the cumulative percentage of problems covered as you move across the bars. This helps you see where the biggest improvements will come from. When we plot this line, we see that underfilled bags account for almost 50% of all issues, while the broken seals make up 31%, and the wrong grind size is only 19%. As we can see here, Pareto principle is telling us that if we fix underfilling and sealing, we'll eliminate 80% of our problems. To sum this up, the Pareto chart helps us focus our energy where it matters the most. Now we dig deeper into the underfilled bags problem. If we want to solve this problem, we need to first understand why does it happen. For this, we use the cause and effect diagram, also known as a fishbone. The fishbone diagram looks like this. If we look here at the diagram, we notice that the fishbone categorizes the possible causes of the problem into main categories, which are machine, manpower or human error, materials, method, and at the end, measurements. Now, depending on the problem, these categories may change. For example, you can add more categories if needed, like, let's say, environment, for instance. You can also delete some of the irrelevant categories. So it all depends on the problem you are trying to solve. Okay, now let's go back to our problem and try to brainstorm potential causes and list them under these key categories. Now, under machine, we could write filler miscalibrated and hopper clogging, for example. At manpower, we can have a not trained operator. Under material, we could have the problem that the grind density varies depending on roast. At method, I will write no standard procedure for recalibration. And at measurement, I will write that the weighing scales not checked daily. Okay, what we have done now is that we have listed all possible causes that may be resulting for our problem, which is the underfilled bags. Notice that this diagram doesn't give us the answer yet, but it ensures we explore all possible reasons instead of jumping to conclusions. Okay, now let's go back to our main problem, and we try to get more data. So we start by measuring the actual weights for 200 packs and plot the weights on a histogram, which will look like this. Now, by looking at the histogram, we notice that instead of clustering tightly around our target of 250 grams, the weights range widely, from as low as 230 grams to as high as 270 grams. The histogram makes variation visible. And in quality management, excessive variation is the enemy of consistency. Now, by the help of the histogram, we now understand the range of variation we have in our process. But we need to know if this variation is predictable or unstable. That's where the control chart comes in. In the control chart, we plot bag weights over time, with upper and lower control limits, with let's say from 240 grams to 260 grams. Here's what we find. Every Monday morning, weights dip below the lower control limit. The control chart shows us the difference between random noise and a real process problem that requires action. Okay, now we look at the control chart side by side with the fishbone diagram, and we try to identify the actual causes resulting for the weights to dip every Monday below the lower control limit. And here, I got a theory. And the theory is that the operator forget to recalibrate the machine every Monday morning, which also results in a coarse grind due to the roast variation. Right? So now we think grind size affects filling weight. When the grind is too coarse, the coffee takes up more space, leading to lighter bags. But up till now, this is just a theory. And to prove our theory, we conduct a little experiment where we fill some bags with coarse grind and some with medium grind and other with fine grind. Then, we weigh the bags. And finally, to test our suspicion, we blot the results on the so-called scatter diagram. So we plot grind size on the x-axis and bag weight on the y-axis. Now the result from the scatter diagram is clear. As grind size increases, bag weight decreases. The scatter diagram confirms one of our root causes: inconsistent grinding. As we can see, by applying all 7 QC tools, here's what we discovered in our coffee factory. The biggest issue is underfilled bags. Causes include machine calibration, grind size variation, and Monday startup effects. Broken seals are the next priority, likely from worn sealing jaws. With this insight, corrective actions are clear. Recalibrate machines every Monday morning, standardize grind settings and monitor density, replace or maintain sealing equipment. The data has spoken, and the path to improvement is obvious.
If you found this video helpful, don't forget to give it a like and drop a comment below. We'd love to hear your thoughts or questions. And if you're into leveling up your skills with expert-led content, hit that subscribe button and turn on notifications. For full courses, downloadable assignments, and certifications, head over to excetify.com. Start learning smarter today.